Hello and good day, students. Let us begin the end. We are going to be starting Chapter 18 today on Wednesday. Friday, we will be continuing Chapter 18, and next Monday, we will be ending Chapter 18. And then we're going to call it a semester. Having said that, we really only have a couple of homework assignments left. So normally I talk about this at the end of the lecture, but let's just address it here in the beginning. Why not? So homework corresponding to this lecture, which is on Wednesday, will be due on Friday. The homework then that corresponds to Friday's lecture will be due on Monday, and that's it. There is a final lecture that will be taking place next Monday, but because then we are going to, that's the last day, lecture day, and then we have Tuesday's Lab 10 is due, and then Wednesday is reading day. We don't really have the time for an additional assignment. So really there's only 2 Chapter 18 assignments, and that's gonna be it. So there will be some material, which we're talking about on Monday, that there is no explicit homework assignment for, but there is going to be plenty of suggested work on the study guide that I will be posting here shortly for Chapter 18. So be sure that you are studying ahead. Look at that study guide as a means to supplement your studying for the final, since the final exam will be predominantly over Chapters 17 and Chapter 18. There will be a review of other material on the final, going all the way back to Chapter 10, but the final is going to be mostly focused on Chapters 17 and 18. Especially since 17 is so detail-oriented, 18 is going to be newer stuff. It's going to be the freshest material in your brains. So yeah, definitely go back, review older material. There will be a wide variety of problems on the exam, but the oldest material will be the more common material from those chapters that we'd seen a couple of times. Okay, so let's get into Chapter 18. No more distraction. So today we are going to be introducing a new concept, a new term, electrochemistry, and then what we're going to do is relate that to an old topic, which is redox reactions. So yeah, let's not waste any more time. Let's just get into it. All right, so electrochemistry. This is the branch of chemistry where chemical reactions either produce or consume electrical energy. So one of the, defining features of a redox reaction, which we introduced back in Chapter 9 last semester, is that a redox reaction involves the transfer of electrons, right? This is redox. And so electrochemistry sort of encompasses redox chemistry, since this is the branch of chemistry that's not just looking at the redox reaction itself, but also the energy, specifically, right, the electrical energy, and electrons define electrical energy. We're looking at the energy that is caused by the movement of electrons throughout this particular type of chemical reaction known as a redox reaction. So that's how all of this is connecting here. Redox reactions we've talked about before. Electrochemistry, now we are going to be looking at the electrical energy component as the electrons are transferring from place to place. In the illustrations below, we see that there are some electric clamps on a lemon. There are some, metallic nails in the lemon, and so we have this positive and negative flow of electrons either going into and out on the other end, and we can see that the voltage of this lemon is 0.906 volts. And so it would make sense if we were to tie 2 lemons in sequence, as we can see here. So now we have electrons coming in, transferring over to the second lemon, and then exiting. We have twice the voltage, right? We have twice the lemons, and the lemons are what are the aqueous solution here. There are plenty of ions inside of a lemon, and lemons are very, very juicy. There's a lot of water to go around, and so it's very easy for the electron that is coming in to transfer and exit there. And so the energy associated with the flow of electrons either through this one lemon or the 2 lemons is going to be what we're looking at here now. But why do we care about electrochemistry? I mean, are we always just like shoving nails into lemons and measuring their electric potential? No. But we are in a very electronic society, right? We live in an electronic society. If it weren't for electrochemistry, I would not be able to transfer this knowledge to you remotely via the internet. Electrical energy is a very wide and growing, a very large and growing field in chemistry, physics, and engineering. The electrical energy is the energy that is resulting from the flow of electrons, which is, what we talked about or just introduced with the term of electrochemistry. And the energy then is measured as a difference between what we call reduction potentials. And we're going to be talking about that term in more detail on Friday, but suffice to say that we have inside of materials like a battery, a positive and a negative end, right? That's why we always see there's this one end that's marked with this little nub, and the other end down below is marked with the opposite sign. And it's the energy difference between this positive and the negative is what we then are going to be calling the electrical energy. Many different applications have arisen from this type of electrical energy, such as dry cells, also known as batteries, like this Duracell that is illustrated on the right. There are lithium-ion batteries that are in many modern electronics like computers, phones, Nintendo Switches. Basically, any small portable electronic device is going to be powered more than likely by a lithium-ion battery. There are also additional forms of energy like fuel cells, solar cells, etc. Like all of these different types of batteries or powering devices are powered thanks to electrical energy. Okay, so if you want to do some more research on batteries, fuel cells, etc., there are plenty of examples in the textbook later on, like in the pages that I had listed on the first slide. The second chunk is all a description of batteries and how it connects to what we're going to be talking about here, which are redox reactions. Okay, so here's where we're going to start our review then of Chapter 9's material, and this is what we're going to be focusing on then for most of today. Starting Friday, we are going to go more in depth then beyond this level, beyond what we're going to be reviewing from previous semester. And then last but not least, next Monday, we are going to kind of tie everything together with a nice little bow. All right, so all galvanic cells, which are types of electrochemical cells, are dependent on redox reactions. And a redox reaction then is the combination of an oxidation and a reduction reaction that always occur together. And the reason why they occur together is that an oxidation reaction, by definition, again, is a reaction that results in the loss of electrons, specifically from reactants to products. Right? It's not that the reaction is just mysteriously losing electrons in an unbalanced way. I mean that there is some type of reactant that is losing electrons, and an electron then is being ejected as a product. A reduction reaction then is any reaction that results in the gain of electrons. And so in a reduction reaction, your electron is going to be a reactant, is going to be absorbed by some other reactant that's present, and then the product is going to be a more negative species. And so we can see why these two reactions occur together, because there's going to be one reaction that is losing electrons, and then another species nearby that's going to be gaining electrons as a result. And so the combination we call a redox reaction. When discussing redox reactions last semester, we only had the time to go into these first two pieces in detail. We discussed what an oxidation number is, what an oxidation state is, that an oxidation number or an oxidation state is a means of electron bookkeeping. You can even put a hyphen in there. It's bookkeeping. What the oxidation state tells us then is from reactants to products, whether or not a species has either gained or lost electrons. The activity series we also had time to cover. The activity series is useful for also identifying whether or not there is a reduction or an oxidation, and whether or not it will spontaneously occur. We didn't do any calculations like Gibbs free energy calculations, energy calculations. We just had a table that is known as the activity series, and we used that to determine whether or not a reaction would spontaneously occur based on what types of reactants were mixed together. We will be reviewing both of these two pieces, but I want to spend most of the day talking about this third bullet that we didn't get the chance to really talk about at all last fall, which is how we balance redox reactions. And the reason why we have, we're going to be spending some detail on this, why we have an alternate method or a more detailed method for balancing redox reactions, is because of all of the movement of electrons. We don't just balance the molecular or elemental species inside of a redox reaction. We also have to make sure that we're balancing charges and that we're making sure that we're not like losing electrons in a balanced chemical equation. All right, so let's just go through all of these points. 1 and 2 we'll hit a little bit more quickly, and then 3 we will spend some time on balancing redox reactions. All right, so first and foremost, we determined or learned to determine oxidation numbers, which I shorthand with this ON. This stands for oxidation number. Oxidation numbers we determine by using the hierarchical rules that we learned last semester. Now the C handout I have listed or written out here because I have posted a PDF to Blackboard that has all of the rules that we learned last semester on it. So if you are stuck at home and you don't have your folder or your notes from last semester, you can still see what the hierarchical rules for determining oxidation numbers are. All right, so as a quick reminder or review, we're going to go through and discuss what the hierarchical rules mean and how we use them to determine the oxidation numbers of the elements in lithium phosphate. All right, so our first step for determining the oxidation numbers in lithium phosphate is to determine whether or not this molecule, or compound rather, is an ionic compound or a molecular compound. Since lithium phosphate contains a metal and a bunch of non-metals, we can determine that this compound is ionic. The reason why this is going to be helpful to us is according to the hierarchical rule or rules of oxidation numbers, the total number or the total charge on your species is going to be useful in determining what your oxidation number for the pieces inside are. Since we don't have a charge overall on this compound, it's going to be useful to break it down into its ions in order to get a better idea for what the oxidation numbers are. So let's break down our lithium. We have 3 lithium pluses, and we have 1 phosphate with a 3- charge. So our oxidation numbers now are going to be a little bit more apparent. According to the, I think it's second hierarchical rule, the charge on an ionic element or an ionic species, like we can see here, is going to be equal to its oxidation number. So the oxidation number of lithium is going to be +1. All 3 of these lithiums that have a +1 charge are going to have an oxidation number of +1. Now we're going to follow the rest of the hierarchical rules from top down to determine what the oxidation number is for phosphate and phosphorus and oxygen inside of this phosphate polyatomic ion. Again, the charge on your molecule, in this case the charge on our polyatomic ion, is the total of the oxidation numbers. All of the oxidation numbers between the phosphate or phosphorus and the 4 oxygens in the phosphate has to equal a -3. Now, if we work our way from top down, we're going to have to find where phosphorus or oxygen are addressed somewhere in the oxidation number hierarchical rules, and we can see that the oxygen is addressed first. And according to the rules, working our way from top down, oxygen is going to have an oxidation number that is equal to -2, unless there is a different rule that conflicts, which in this case, there's nothing that we've seen so far that conflicts. So all 4 of these oxygens are going to have a -2 oxidation number, meaning that there is a total of -8 in terms of like negative charge or negative oxidation number. And so the oxidation number of phosphorus, which is kind of our X right now, it's our unknown, minus the 8 from all of the oxygens that are present here is going to have to equal the total on the phosphate ion, which is -3. What this leads us to believe is that the oxidation number on our phosphorus, our X, where do I want to write this, is going to be equal to a +5. And so in following the method of the hierarchical rules of oxidation numbers, we can break down what our compounds are, whether they are ionic or molecular. If they're molecular, we're just going to keep following down the rules. There's nothing that we have to break up, no ions we have to consider. And normally it's the hydrogens and the oxygens where things get to be a little bit tricky when it comes to determining oxidation numbers. But if we follow the rules from top down, hence why they are known as hierarchical rules, we should not have any real problem finding what our oxidation numbers are. We are going to be getting plenty of practice revisiting this for the homework that's going to be due on Friday, but if you do have any problems, do not hesitate to let me know. All right, next this brings us to the activity series, which is what we can use to predict whether or not reactions of mixed elements are going to occur, or at least a redox reaction, if that is going to occur. So the activity series is used to predict whether a metal will spontaneously be oxidized by a different ion or an acid that might be present around it. According to the activity series table, which is table 9.6 in the text, going up the table, we have an increasing ease of oxidation. That's what our x-axis means here, oxidation. So lithium is going to be the element that is the most easily oxidized of all of the elements in our activity series. What this means is that lithium is going to be the most likely of all of these elements to just jettison off an electron if it gets the chance. If we work our way all the way down further on the table of the activity series, we can see that gold down here is going to be the least easily oxidized. In other words, this is going to be the most easily reduced element. Gold is not going to give off 3 electrons very easily. In fact, the reverse of this reaction is going to be much easier, where gold is going to, in its 3+ charge, prefer to be reduced by 3 electrons to become elemental gold. And so if we partner up different either elements or ions, we can question whether or not we're going to get a spontaneous redox reaction. So for instance, if we had 3 lithiums in their solid form, and mixed it or just added it to a solution of gold 3+, we would very likely see, assuming like room temperature, standard conditions, that there are going to be 3 electrons from these 3 lithiums that are going to be transferred over to our gold. This is going to give us 3 lithium plus in aqueous solution and a gold that will crash out as a solid in solution. So this we would expect to be a spontaneous process due to the increasing ease of oxidation that is presented here on the activity series. We will be putting some specific energies to these reactions, these half reactions, a little bit later, but we're going to be waiting until Friday to talk about that and be tying some specific energies in. For now, we're just going to be looking at how qualitatively we can use the activity series. All right, but this is going to bring us to the big beefy monster of the day. Personally, I don't think that these types of problems are as difficult as titration or ice table problems that you guys have been working on, so hopefully this will be a little bit of a reprieve, especially because all you have to do to balance a reaction or a redox reaction is follow the steps. So here are the 7 steps that we're going to be learning to balance a balance a redox reaction, and this is known as the half reactions method. The reason why it's called the half reactions method is because of what we do in step 1. And I'm just going to be kind of describing these steps, and then we'll work through an example to see explicitly how they work. So our first step is that we're going to look at the redox reaction and identify, using our oxidation numbers, what the oxidation and reduction steps are. Which species is being oxidized and which species is being reduced. Then we are going to take our redox reaction and split it into 2, where one reaction is going to be the oxidation step, and the other is going to be the reduction step. The reason why we split these up is it becomes easier to keep track of electrons if we're just looking at, okay, we have, let's say, lithium here, and we know that it loses 1 electron. So it's going to be easier to figure out like what the electrons are that are coming off or going into the oxidized or reduced species, respectively. Next, we are going to balance all atoms except for oxygen and hydrogen. The reason why we save oxygen and hydrogen for a different step is because in aqueous conditions, which is where a lot of these redox reactions take place, in aqueous conditions, much like we've seen for acid-base chemistry, the water gets involved. Because water is the solvent and there is just an abundance of water in an aqueous solution, the water is going to get involved. It will act as either a carrier for electrons, or will be generated, or will be used up in some way in a redox reaction. So we actually save balancing the oxygen and hydrogen pieces due to the water for steps 3 and 4. We're going to be balancing all oxygens present by adding waters to the opposite side, and we're going to be balancing hydrogens present by adding an H+. All right, the next couple of steps then, we finally balance the electrons or charges with the electrons. We then scale the reaction so the number of electrons that are being produced and used are equal to each other, and then we add the reactions back together, and we should have a nice balanced reaction where elements are balanced, charges are balanced, we have a complete redox reaction. All right, so let's see this half reactions method in action. So what we're going to do is we're going to assume that the following reaction is spontaneous. We're also going to assume that it is a complete reaction. Reversible redox reactions can get to be a little bit tricky to work with physically, though the way that we use to balance them is the exact same. But we're going to balance the following chemical equation. So what we can see here is there is a redox reaction occurring between our iodide, our chromate here, our Cr2O7 with a 2- charge. This is going to be transforming or turning into chromium with a 3+ charge, and free iodine I2 with no charge. All right, so our first step, going back, I'm just going to keep going backwards to refer to the half reactions method so we can kind of follow these steps. So our first step, we are going to identify the oxidation and reduction reactions. In order to do that, we have to figure out what the oxidation numbers are on each of the species in this reaction. So let's just start on the left. According to our hierarchical rules of oxidation numbers, if you have an ion that is a free ion like so, the oxidation number of the free ion will be equal to its charge. So we would expect the iodide here, I-, to have an oxidation number of -1. I'm actually going to come back to this chromate in a little bit. Let's move on to the next free ion that we see, since it will follow the exact same rule as the iodide. Since it is a free ion, its oxidation number will also correspond to its charge. So the oxidation number of this chromium is going to be 3+. The first rule on our hierarchical rules of oxidation numbers states that any free element is going to have an oxidation number that is equal to 0. And that is because this species has no charge. Really what the oxidation number or oxidation state is an approximate measure of is of ionic charge. Even if you're looking at a molecule, it's going to predict some type of ionic charge. So if you're looking at a molecule that literally has no charge and it's the same element, it's not like one of these iodines could have a +1 charge and the other can have a -1 charge. That wouldn't make any logical sense. And so we say that both have an oxidation number that's equal to 0. Okay, with that, we are going to come back around to our chromate. So there's going to be our chromium here and our oxygen here. Both of these two elements are going to have an oxidation number that is unique to themselves in this compound. The oxygen is higher up on the rule than chromium, or higher up on the hierarchical rules, where transition metals aren't even explicitly mentioned unless they have some explicit ionic charge, like the chromium with the 3+ charge on the right. We don't really have a rule specifically for transition metals, and that's because they, much like carbon, which is also not listed, just kind of take whatever electrons they get, all depending on what the other elements are inside of the molecule. So we're going to focus on the oxygen first. According to the hierarchical rules, each of these oxygens is going to have an oxidation number that is equal to -2. Now, because there are 7 oxygens in this molecule, this means that we are going to have a total of a negative 14 charge, where each of these 7 oxygens is bringing a negative 2 charge to the table. Negative 14 then is going to be our total there, right? Negative 14. Each of these chromiums, each of these 2 chromiums, so I'll say 2, I don't know, chromium. We'll just keep Cr as our unknown variable here. Each of these 2 chromiums is going to have its own oxidation number, so we're going to have to take that into account, much like how we have all 7 of our oxygens taken into account with our negative 14 here. But the total of this sum is going to have to equal negative 2, since there is a charge of negative 2 present on our total ionic polyatomic ion. So if we move our 14 to the other side, plus 14, this gives us a total of a positive 12 here. And since we're solving for the oxidation number on each of the chromiums, we should divide this by 2, which gives us an oxidation number on each of the chromiums that is equal to plus 6. So our oxidation number here is equal to plus 6. All right, that's cool. Let's talk about what information that actually gives us in accomplishing the first step of balancing a redox reaction. Well, what we're looking for, again, is whether or not a species is being oxidized or reduced. Since there is no oxygen present on the right-hand side of the equation, we are going to assume that it is not the species that is being oxidized or reduced. Instead, what we are going to look at is the chromium and how it connects from reaction or reactant to product in this reaction, and our iodine and how it transforms from reactant to product. What is the difference in the charge? So we can see that our iodide goes from an oxidation number of -1 to an oxidation number of 0. This means that it has lost negative charge. And if it has lost negative charge, it must have lost electrons. And if it's lost electrons, well, by golly, that must mean that that is our oxidation step. It is the iodine that is being oxidized over the course of this chemical reaction. The chromium we can see as a reactant started with a +6 charge, and over the course of the chemical reaction, it dropped to a +3. Notice that any type of gaining of electrons doesn't mean that your species is going to end up being a negative ion, right? We went from a high positive number to a medium or moderately high positive number, but we still lost positivity. And if we lost positivity, that must mean that we gained some negativity, which means that we must have gained electrons. And if we gain electrons, well, by definition, this is a reduction step. So it is our chromium that is being reduced over the course of this chemical reaction. It's the iodine that is being oxidized. It is the chromium that is being reduced. All right, so if we go back to our list of rules, in order to balance this chemical equation, then what we are going to do is break our reactants down. Our oxidation is going to be one half reaction, and our reduction is going to be the other half reaction. All right, so I cleaned up the slide, but we just identified that the iodine is what was being oxidized, and it's the chromium that's being reduced. So what we're going to do is pull the reactants and products corresponding to each of these separate steps in and organize them in their own chemical equation. So we're going to take the I- that is aqueous, and it is transforming into the I2 that is aqueous, and kind of gather that as one chemical reaction. And then we are going to take the Cr2O72- that is aqueous, and that is turning into the chromium with a 3+ charge in aqueous conditions also, and that's going to be a separate reaction over here on the right. All right, so to go back to our rules, step 1, complete. The rest of the steps should follow pretty quickly, since now we are actually just following steps. So we're going to balance all atoms except for the oxygens and the hydrogens. So on the left-hand side, we can see that, or left-hand reaction, our oxidation reaction, we can see that we have one single iodine on the left, and we have an I2 on the right. So we're going to balance the iodine on the left by adding a coefficient of 2 in front of it. Similarly, the reaction that is on the right with the chromate, polyatomic ion, and the chromium with a 3+ charge, we can see that there are 2 chromiums inside of the polyatomic ion, meaning that we must also have 2 chromiums as a product. So we're going to put a coefficient of 2 there. We can see that all of the elements that are not oxygen and not hydrogen have now been balanced. So check. Next, we're going to balance all of the oxygens by adding waters on the opposite side of the reaction. Our first reaction, the oxidation step with the iodines on the left, has no oxygen present, so there's no reason to add any water to this reaction. The reaction on the right, we can see that we have 7 oxygens in this Cr2O7 2- polyatomic ion. So we're going to have to add 7 waters to the opposite side, the product side, in order to balance all of those oxygens out. What this means is that in the big picture, as this polyatomic ion is breaking down and is being reduced to chromium 3+, all of the oxygens that are being lost by the polyatomic ion are turning into water. A check. Next, we're going to balance all hydrogens with H+. So we go back to our reaction. Our first reaction, again, the oxidation, there's no hydrogen here, so we're just going to skip over that step for the iodine or the oxidation reaction. If we turn our attention then to the reaction on the right, we see that in writing our 7 waters, we have also written out or added 14 total hydrogens to the product side, which means that now on the reactant side, we're going to have to add 14 hydrogens, and these are going to be in the form of H+. The insinuation being that we are now combining a bunch of acid, a bunch of free-flowing H+ ion in solution to this polyatomic ion, which is then breaking down or decomposing. It is turning into the chromium ion along with 7 waters, again, that are being generated. All hydrogens balanced, check. Now we need to balance some charges with electrons. This is the crux of any redox reaction. It is the electrons ultimately that we care about, since these are the defining feature of our redox reaction. So we have to make sure that the total number of electrons that are being generated and produced are going to make sense. They're going to be equal, that there's going to be a reaction that is not ultimately gaining or losing electrons, that we are adhering to the premise of the conservation of mass. So our reaction that is on the left, we have 2 iodides. We have 2 negative charges on the reactant side. What this means is that we're going to have to add or balance the negative charges on the left-hand side with an equivalent charge on the right-hand side. And just to make sure that I'm not writing like 2 reactions that are running into each other, I'm just going to do kind of like this caret with 2 electrons coming in, but it should be understood that these 2 electrons now are being produced as the iodide is losing charge and is oxidizing to become iodine. These 2 negative charges have to go somewhere, and they become product on the right-hand side. The total number of charges on the right-hand reaction, this reduction reaction, can get to be a little messy, so let's observe reactant and product separately, since we're looking at the difference of the charges between the reactants and the products. So the total number of charges we have on the reactant side, there are 14 plus 1s, and there is 1, right, since there's a coefficient of 1 in front of this chromium here, there is 1 minus 2. So we're taking 14 minus 2 to give you a total of 12 positive charges on the reactant side. And on the product side, we have 2 plus 3 charges. Water is completely neutral, meaning that we have a total of a plus 6 on the product side. Over the course of this reaction then, since we went from a total of plus 12 on the reactant side to a total of plus 6 on the electron side, well, there must have been 6 electrons, 6 negative charges that were gained in the process of this reaction occurring, this reduction on the right. So if we take a positive 12, and if we subtract 6, right, if we add 6 negative charges, this is going to give us a total of a positive 6, meaning that there are 6 electrons that are being gained as a reactant. We can kind of insert them right there in our overall equation, or I guess, since there's an aqueous thing, we can insert them right there. All right, so all of our charges have now been balanced with electrons. Our second to last step, and really the last step that's like actual work, we have to scale our reaction so that the coefficients on the electrons are going to match. The reason why we want to do this, again, is to make sure that all of the electrons that are being generated by one of these half reactions is being absorbed by the other half reaction. So we can see that the reaction on the left, our oxidation reaction, is generating 2 electrons, and the reduction reaction requires that there be 6. These are the 2 coefficients that we need to be equal. We need there to be a total of 6 electrons being generated in order for this redox reaction to occur. So what we're going to have to do is scale up our oxidation reaction by a total factor of 3. So this coefficient of 2 is going to have to be multiplied up by 3 to become a 6. We're going to have to multiply the coefficient of 1 here by 3 to become a 3. And this 2 then also gets scaled up to become a 6. In doing so, the coefficients in front of these numbers of electrons match. So as this reaction, this oxidation reaction progresses a total of 3 times, we're going to be generating a total of 6 electrons in the process, and those 6 electrons are going to be what fuels the reduction of the chromate into the chromium and producing a bunch of water around it. All right, step 6 is complete, which means that the very last step now is we are going to add the half reactions together. Whoop, wrong direction. The half reactions that we add back together then are the reactants and products for these 2 things that we balanced separately. So we're going to take the reactants and add them to the reactant side of the, like, an overall reaction. And then we're going to take the products from both and add them together so that we have kind of this sum of products for an overall chemical reaction. And what this is going to look like, I'm just going to write it like in kind of the space up on top because I don't want to lose all of this writing down below. We're going to start with our 6 iodide ions that are aqueous. So check, that's been added. The other remaining species from the oxidation reaction are products, so we're going to hold off until after the arrow to write those. We're going to add then the rest of the reactants from our reduction half step. So we have 14 H pluses that are aqueous. We have a chromium 207 with a 2 minus charge that's aqueous. And we have a total of 6 electrons that are necessary to push this reaction forward. And with that, all 3 of the reactants from the reduction step have been taken into account. All right, our products then, we have 3 I2s that are aqueous, and that's and as well as the total of 6 electrons that are being generated by this oxidation. So check, all of the oxidation species have been taken into account in our overall balanced redox reaction. And last but not least, we have 2 chromiums with a 3 plus charge. These are aqueous, as well as a total of 7 waters that are in liquid form. And this now is our overall balanced redox reaction, where if we were to add up all of the elemental species, they should be completely balanced, as well as if we added up all of the charges on the reactant and the product side, those should be equal as well. Commonly, we don't actually include then in the final overall reaction the electrons, since they cancel out, right? We have them both present as reactant and product. Sometimes you'll see them present. Sometimes you'll even see it as I have it illustrated now with them present, but with a slash through them. All of those are kind of equivalent and generally conventional representations of a balanced redox reaction. The method that we just learned was the half reactions method, either in acidic or neutral conditions. But how is it that we can have H plus exist in a basic solution? Well, the answer is that it is in equilibrium with water, but generally we think of H plus as being neutralized by any OH minus that might exist. So we actually have a slightly modified version of the half reactions method if we are working with basic conditions. And the only real difference is that we have an additional step right here, which is that we're going to neutralize all H plus that is present by adding OH minus to each side of the reaction and kind of canceling them out. We're going to perform a neutralization in between all of the steps that we just learned to follow. All right, so let's look at an example of the half reactions method in basic conditions as well, just so we can see that one step in action. All right, so we are going to observe this reaction. We're just going to start from step 1. We're going to identify what is being oxidized and what is being reduced. So our silver that is present here, the Ag solid, is a free element, no charge present, meaning that its oxidation number is equal to 0. The zinc is a free ion, so the charge on the zinc is going to mean that it has an oxidation number that's equal to the charge of +2. Silver oxide is an ionic compound, and so we're going to assign the charge of both of these species in the ionic compound to be their oxidation numbers, which is a -2 for the oxygen, and each of these silvers is going to get a +1. And last but not least, the zinc, which is free zinc, is going to have an oxidation number that is equal to 0 since it is a free element without a charge. And if we connect the elements then to determine which is being oxidized and which is being reduced, we can do so. Where again, oxygen's not present on the left-hand side. It is assumed that it is not one of the reactants in the redox reaction, but rather is a byproduct of the aqueous solution. And so the silver, we can see, goes from a charge of 0 to a +1, and the zinc goes from a +2 down to 0, meaning that it is the silver that is being oxidized. Since it is gaining positive charge, it must be losing negative charge. It's losing electrons. The zinc is going from a +2 down to a 0, which means that it must be gaining some negativity. It is being reduced. Oh, wrong direction. All right, first step is complete. We have identified the oxidation and the reduction steps. We are going to split these two pieces in two. All right, so I'm going to split these two reactions into like so. So we're going to have the silver is transforming into silver 2 oxide, aqueous, and the zinc with a 2+ charge is transforming into zinc solid. All right, so here are two half reactions that we're going to balance. All right, so to go backwards, we're going to balance all atoms except for the oxygens and the hydrogens. There's only one thing that we need to balance, and it is the silver in the first reaction. Since we have 2 silvers present here, we're going to have to add a 2 in front of the silver as a reactant to make sure that that is balanced. So step 2 is complete. Next, we have to balance the oxygen with waters and all of our hydrogens with H+. So the oxygens that are present, there's only one that is a product in the silver reaction. So we're going to add an H2O as a reactant here to balance out that one oxygen that is present. We are now going to add in also 2 H+, since there are 2 hydrogens in the water that is present on the left. It is these 2 hydrogens now that pose a little bit of a logical problem, since we are working again in basic conditions, and H+, which represents strong acid being present, kind of floating around, we know that strong acids and bases neutralize each other, so what we're going to have to do is represent that by neutralizing our H+, by adding OH- to each side of the reaction. So if we add or OH- to one side, in this case, since we have 2 H+, we're going to add 2 OH-. We're also going to add 2 OH- to the other side. What this means is we're going to have 2 OH- now present, representing a reactant that is necessary in this reaction, and these 2 H+ are going to be neutralized by these 2 OH- to give us 2 waters that are present. All right, if we want to clean this up a little bit, since now we can see that we have a water present on the left-hand side and 2 waters on the right-hand side, we can actually cancel one of these waters out if we cancel out one of the waters that is present as a product. So now our general reaction, I can clean it up a little bit just to make it a little bit more straightforward. We have 2 hydroxides, which are being combined with 2 silvers that are in a solid form. And this is going to create some silver oxide, AQ, as well as generate a molecule of water. So this is what our oxidation reaction right now looks like. It is symbolizing, if you were to take a chunk of silver and throw it into a basic solution, you would see this like silver oxide solid potentially form, but would more than likely exist in aqueous conditions, as well as you would see a change in the water concentration. All right, we have completed now the additional step. Next, let's balance the charges. We're going to scale the half reactions, and then we're going to put these half reactions together. All right, so next we are going to determine the charges. So if we look at the reaction on the left, we can see that we have 2 negative charges on the reactant side, and we're pretty neutral on the right-hand side. So we're going to have to balance those 2 negative charges by adding 2 electrons as a product in the oxidation reaction. This makes sense. Since there is an oxidation reaction occurring, your electrons should be present as a product. The reaction that was on the right, this reduction reaction, should have electrons present as a reactant, which is exactly what we need to balance this reaction. Since we have two positive charges on the zinc, we're going to need 2 negative charges on the left-hand side to balance out the neutral charge of the neutral zinc on the right. Our next step in balancing the redox reaction is to scale the electrons to make sure that they are of equivalent number. They already are, right? We have 2 electrons present that are being produced from the oxidation reaction, and we have 2 electrons that are being gained in the reduction reaction. So we don't actually have to do this step. We can totally skip it. There is no scaling that we have to do since it is already just done. Our last step then is adding the half reactions together, and we can call this reaction balanced. So we're going to take all of our reactants and put them on the left-hand side of our overall chemical equation. We have 2 hydroxides being mixed with 2 silvers in a solid form, along with a zinc with a 2+ charge and 2 electrons. And this will then transform via the transfer of the electrons from the silver that are being generated in the previous reaction. We're going to end up with some silver to oxide, aqueous, some water in liquid form, 2 electrons, right, that again are being produced by the oxidation reaction, as well as some zinc solid. And this is our overall balanced redox reaction in basic conditions. So we have the 2 hydroxides, which are now causing mediating this redox reaction between the silver and the zinc, as the silver is losing 2 electrons and it is the zinc that is gaining 2 electrons. All right, and that's all we're going to talk about today. So the bulk of what we've introduced here is a combination of just general definitions and review from Chapter 9. So here we have some suggested problems for balancing redox reactions. I'm going to more than likely also assign some throwback problems from Chapter 9 that are maybe a little bit easier just to get you guys on the right track, right? Taking the correct first step in learning to balance these redox reactions. All of the big announcements I gave at the beginning of lecture today, so I have nothing additional really to say. So class is dismissed.